signal processing, and later on, I will move to the wireless communication application. So what we see now with the digital signal processing design is that much of the signal processing application are more and more moved to the digital domain. So previously solutions required multiple stages of filtering, mixers in order to translate the input signal to a baseband frequency. So what we see now is that the hardware vendors themselves are including some high-speed ADCs that are running above 1 gigahertz, something that's more and more. We are having a higher and higher speed with ADCs and a newer generation of these boards. In order, these hardware vendors are trying to answer the need also of their customers. So we know that a lot of the algorithms and IPs are moved to the digital part, a digital domain instead of the analog domain like we had previously. And if we go back to the concept of model-based design, what we usually see with or what we saw with our model, our customers, is that they used to use MATLAB in order to develop algorithm, of course, and validate this algorithm in MATLAB. And later on, they will use this algorithm in order to use it as a specification document. So they use this algorithm as a specification document. They give it to the hardware designers or engineers, and the hardware designers, they will start like writing their hardware structure or the hardware, the HDL code by hand, go to the integration and test. And we noticed that this traditional hardware design will lead to longer iterations, right? And that's when where some of our like application-oriented toolboxes could answer some of your needs. Here, for example, we are talking about the DSP HDL toolbox. So how we can use the DSP HDL toolbox or these kind of toolboxes. So let's say you keep your algorithm or algorithm development phase in MATLAB, where you can develop your algorithm, validate it, and you can use it as a golden reference this time in order to compare the result that you have in your algorithm and what you will be having later on in your architecture. So when I say design system architecture, it's more about like exploring the streaming algorithm compared to what you have with a frame-based algorithm in MATLAB. You can, of course, also explore some hardware implementation detail that you have. And you can leverage some proven IP blocks. When I say proven IP blocks, they are the IP blocks that are coming with the DSP HDL. We'll see them later, and we see how they can show us, of course, the trade-off that we could have in simulation and later on in implementation. So in the design system architecture phase, we will be exploring all these options that we have. We'll privilege Simulink, the DSP HDL toolbox, and of course the fixed point designer that will help us to go to converge for a fixed point representation of our model. All of that, of course, we can also use the continuous testing and verification that we have, and we can privilege the back-to-back testing between the golden reference and the design in Simulink, and later on what we have in Simulink and what we could have after we generated the code and implemented the code on the hardware. So we keep the same concept of model-based design, but we are adding a very application-based layer, which is the digital signal processing HDL that we have here. Another note on the challenges that we have today with the high-speed application design is that we know that implementing scalar signal processing at a gigasample per second would require the FPGA itself, the FPGA clock itself to run at gigahertz. And having a gigahertz clocks where clock rates at least will significantly increase the power consumption. So we know that FPGA and ASIC clocks are not keeping up with the increasing demands of the single signal bandwidth, which lead us to of course, always the same conclusion is that we need a new class of DSP algorithm that could be implemented on hardware and that can process the wideband data in parallel with efficient hardware resource usage, of course. So we need to have a new class of DSP algorithm that have this trade-off between keeping up with the high-speed demand and the hardware resource usage. And like I said, DSP HDL toolbox will provide some proven IP blocks. For example, here you can see in the library that you have some subsection that's for example, is just for filtering, where you could have some like the classical or the state-of-the-art filters that you can use. And with the DSP HDL toolbox, what you can do is simulate not only the algorithm in Simulink, but also the hardware implementation of the algorithm. So you will start comparing streaming data between scalar and frame. You will even be able to simulate the latency that is introduced with this block. And finally, you could explore the implementation options that you have for each IP. So if you have a new application that you want to develop, you know that it will take time due to programming limitation and the lack sometimes of design engineer resources. So what we offer is going from MATLAB to Simulink or from MATLAB to hardware design by simulating the DSP algorithm and later on generating the code. And that's where we can start talking about the trade-offs that you have. If we can take the example of an FFT, which is not a block that's easily designed, you can see here that for each architecture, you will be having a different latency. So why is that? Because in the first one, we chose to have some fewer resources used, hardware resources used, but we will be still limited with the throughput. Here we are achieving a single, we are achieving with a single data stream, a megasample per second throughput. On the other hand, we have another trade-off that we can have where we be able to achieve a gigasample per second throughput with a parallel data stream and a lower latency, but on the other hand, we'll be using more resources. So the idea behind the DSP-HDL toolbox is to be able to simulate the effect of our choice, our implementation, before going to even generating the code. So you will validate your choices in Simulink, in simulation. Later on, go through code generation, where you can also validate your choices in simulation, and we'll see how we can compare what we have in Simulink to what we have in generated code. So I will dive in a little bit in the FFT because it's a very there's a very high demand on this type of blocks. So if we go and see here in this short video is that you have the FFT, the same block, but you can choose between two types of architecture. And later on, you can have your choice between, you can have the choice of the architecture or even the vector input size, depending on your constraint and on your requirements also. So you can, the result that you see at the top, at the bottom is there is the post synthesis result. It's for a Zinc UltraScale Plus. So you can see between minimizing the resources, low latent, or having a low latency block or a high throughput block, we have a different, we have a different percentage of utilization on our hardware design. And this is like related only to the FFT. So you can imagine what you could have if you have like a complete model. It will give you a lot of visibility on what you will be having later on in your model. So for the first one, when we were trying to minimize resources, we had a high latency, but we had a very low utilization percentage. When we started to reduce latency, we were able to do that. But of course, we started to going up on the usage of the hardware resources. When I say resources, I'm not talking about one resource in particular, but it's mainly like DSPs, LUT, and registers. And finally, when we wanted to achieve the gigasample per second throughput, we needed to reduce the latency, of course, but also increase the vector input size, where it was 1 for the first two examples. Here we start processing a parallel N8 vector input size. So that's an example of what you could have with DSP HDL. Like I said, there's a lot of IPs that are tested, and even in our documentation, you can go and see every block. And usually you have some metrics like you have here for every architecture that you are choosing. And even they will, you will have access to what your IP is implementing. So you will have also the traceability of, and even the knowledge of how the implementation is done in your IP. So that's what I wanted to show you about DSP HDL. I think it's a very powerful toolbox. The DSP HDL, it will save you a lot of time. It will give you like a high-level implementation for your blocks.